Okay. All right. So I just put together a few short slides and forgot to update the date to tell you a little bit about JIT compiler logs, what they are, how you can generate them, and a little bit of a brief dip into what they actually look like. So JIT logs are basically just follow along the basic compilation process, which I've shown on the right side here. And essentially the log documents everything that the compiler does across these three major phases. So what are those phases? Quickly are just, so the first phase is generating the intermediate language for the Testarossa compiler. That intermediate language comes from the Java bytecodes of a particular method. And then that intermediate language feeds into the optimizer, which is a traditional compiler just pipeline of different optimizations, trying to analyze the code and improve the code and ideally make it better. And then finally, that intermediate language flows into a code generator for a particular platform, the platform that you're running on. And it converts the intermediate language into the native instructions of the target platform, and then stores that code into a native code cache so that it can be used when that method is called by other functions. So how can we generate a compiler log to tell us what's going on throughout that process? So the basic command line option is off of the -x JIT option. I've shown here an example version here, which uses a method spec, which is also called an option set, to apply a set of options to a class of methods that's identified by the method spec, which is kind of a simple regular expression. Now, I put regular expression in double quotes because it's not really the formal definition of a regular expression. It uses star to replace any number of characters, question mark to replace one character optionally, and so it's not a real regular expression, but it can be used to specify any class.method combination. And then the options in single parentheses here are applied to whatever methods match this specification. So normally you would try to match this to a particular method that you're interested in, and then you would generate a log. So what are these options in a bit more detail? So the first option is the log equals, which is really just specifying a file name where you want the log information to be dumped. As I mentioned in the verbose log lightning talk, this name is going to be automatically appended with process ID, a date and a time, because if you happen to be running in a system that has many JVMs running at the same time, or even just two, it can get pretty confusing if they're writing to the same file, so it automatically smurfs the name so that that won't happen by default. If you really want it to go into that exact file name, you can use the disable suffix logs option, which will override that behavior. So we got a file name to dump stuff into. The trace full is one of a large number of options that are available to try to control how the logging happens. So trace full is sort of the default starting point. It logs what happens in IL generation. It generates what happens during each optimization and what happens during code generation, but it doesn't go into all the detail that's possible. It doesn't do detailed tracing on any particular optimization. It just kind of documents what's going on. So, but it does a few interesting things here. It will number each optimization, which can be used for problem diagnosis, because there are options that you can use to try to control how the compilation happens later, to include or not include optimizations. It will show the IL trees after any optimization that does transformations. So if anything changes, you'll see what the changed IL is after those changes have been made. It will also list and number the individual transformations that are performed on the code, which again can be used later. There are options that you can use to feed those numbers back into another run of the compilation to do problem diagnosis, to try and narrow down which transformation actually causes a particular effect that you want to fix. And also the code generation major phases are also shown with all the trees and the instructions and how the instructions are generated from each tree, along with how the registers are assigned and so on. It will show you the final generated code. So it has a thing called a mixed mode disassembly, which tries to link what the bytecodes are with all of the instructions that are being generated. And finally, so that's kind of the starting point for tracing, but you can actually, each individual optimization typically has a more detailed tracing options available, which it outputs even more detailed information about what's happening during a particular optimization pass. So the files that get generated using just this option trace full can be 100 megabytes just for a single method. Just because of the level of detail that's being provided here, and because optimizing a method can run, for a scorching compile, for example, it could run 200 optimizations through the course of compiling that method. So there's quite a lot of stuff here, even in a trace full output, but then there's an even a higher level of detail that you can request once you've decided that a particular optimization is of interest. So I don't have time to go into a whole lot of detail about what a JIT log looks like, but I'll just break it down into its sections. It kind of looks like an XML document, but it's not really an XML document, so don't be thrown by the fact that it does claim to be XML. The basic section, so the whole compile for a method is included in a compile and compile stanza from XML. It gives you some information about what method it is that's being compiled and what its hotness level is. Remember that the OpenJ9 just-in-time compiler compiles at any number, well, six different optimization levels, from no-opt, cold, warm, hot, very hot to scorching. And then the three sections of the three sort of major sections of the compile are documented in individual sections. So the generation of intermediate language from bytecodes is in a section called ILGen. Again, the method is there, and then there'll be details about how that intermediate language generation is done. And optimize, sorry, I got the color wrong here, should have been green for optimize, also documents what the method is and its hotness, and then it will show that sequence of trees, as I mentioned, and any sequence of optimizations and what the trees look like when any change is made. And then finally, there'll be a code gen stanza that shows how the code is generated, again, with the method and hotness. There's a section here, in particular, the instructions section, which will show that mixed mode disassembly that I talked about, which basically gives you the final assembly language, or annotated assembly language for what code was actually generated for this method. So again, I don't have time to go into more details than that, I'm afraid, but that gives you the basic section, so you can kind of dig around a little bit if you're interested. And that's basically it for this presentation. There's lots of places where I could go in the next presentations. I could talk more about how the IL is generated. I could talk more about the optimizer section of the log. I could go into detail about how the code is generated, or I could talk about diagnosing JIT problems using the logs, and as I mentioned, using the numbered optimization passes and transformations that are being applied. So I'll pick an order for these if you're not going to give me any input, but if you're interested to learn about anything specific, feel free to drop me a line and let me know what you're interested to hear. And that's it.
Thanks, Mark.